Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last lecture, we started with the region elimination methods and we discussed two such methods which are interval halving method and Fibonacci search method. In these two methods, we observed that the interval halving method can reduce or eliminate region by 50% in each iteration. However, it requires more number of function evaluations, as we saw that in each iteration it is going to require at least two function evaluation, and if it is in the first iteration it requires three function evaluations. On the other hand, the Fibonacci search method requires only one function evaluation in each iteration, except in the first it requires two function evaluation. However, the Fibonacci search method could eliminate only about 38% of the region. So if we look into the efficiency wise, the amount of region being eliminated, we find that the interval halving method is better because it is eliminating 50% of the interval. Whereas if we look into the number of function evaluation required, we see that Fibonacci search method is quite efficient as it requires less number of function evaluation. But in the Fibonacci search method, we also notice that we have to estimate the Fibonacci number in each iteration, and this estimation could be an additional burden in the computational process. So today we are going to look into a method which is very similar to Fibonacci search method and which requires only two function evaluation in the first iteration and subsequently requires only one function evaluation in the following iterations. We'll also look into another method which is very similar to the interval halving method. However, it does not require as many number of function evaluation as it was in the interval halving method, and it could reasonably eliminate the interval at a faster rate. Let us begin with the two region elimination methods. The first method we'll discuss today is known as golden section search method. This method is very similar to the Fibonacci search method. However, it does not have the limitations of the Fibonacci search method where we were required to estimate the Fibonacci numbers. So let us see the golden section search method. In this search method, we first linearly map the interval between 0 and 1, and then we try to find out 2 points at a distance tau from each end of the interval. Then one of the region with a distance 1 minus tau is eliminated using the region elimination rule, and this is done after evaluating the function value at that point. So once we do that, the point which is retained within the region is going to reappear in the second iteration. So again, when we divide the remaining search interval into 2 points, we'll find that the previous point reappears in this case. So we have to choose the tau value in such a way that it can reappear. So it is important to find appropriate tau value, and for that purpose we'll look into the graphical representation to understand the calculation process. So in this graphical representation, you will see that the 2 points which are indicated as this one and this one are actually tau distance from the two boundary which is here and here. This boundary was mapped to 0 and 1 no matter whatever the boundary width is, it is going to be mapped between 0 and 1. And once we do, then we find 2 points which are tau distance from this boundary. And the remaining distance, for example, in this case, this point is tau distance from this boundary, and the remaining distance, this one, is going to be 1 minus tau. So if we eliminate either this or this, we are left with the interval of width tau. And here again, if we find the 2 points based on the factor tau, we need to ensure that this point exists. So if we eliminate this portion, we are retaining this portion, and within this portion we have one point which is here, and this point, if we try to find out from the new upper boundary, this should be tau times this distance, the revised distance. Let me name it as L1 and let me name this as L0, which was the previous distance of the boundary which was set to 0 and 1. So this L1 is equal to L0 times tau. Since L0 is 1, so this is going to be tau, and then we are finding out the point within L1. For that, we are multiplying with the available boundary distance, which is L1, and this is going to be hence tau times tau, and this is exactly going to be 1 minus tau, which is the leftover distance. So this is, if we want to equate it to 1 minus tau, we get this formula, and if we solve this formula, we'll get the tau value as 0.618. This is known as the golden number, and if we use this golden number, we can retain 1 point no matter how many times we remove the 1 minus tau portion. Within the remaining portion, we will always find one of the point from one edge available for the next iteration. So if we look into the algorithm, in the very first step we find the lower and the upper bounds, and then we normalize the search interval W using this formula, where the lower bound AW is going to be 0 and the upper bound BW is going to be 1, and in this case we are going to get the length of the search interval as 1. Then we need to choose a very small number to represent the precision of the result obtained. Once we do this, we need to find out the 2 points at which we need to evaluate the function and apply the region elimination rule. For that purpose, we are finding the point W1, which is going to be the lower bound plus 0.618 and the length of the search interval, and W2, which is, if we are taking it from the other end, BW, which is the upper bound, minus 0.618 times the width of the search interval. And at this 2 point, we want to find out the function values. If you notice the function value, here we are writing it as W. However, our original objective function is with respect to x. So it needs to be transformed appropriately using this equation and obtain the function value for the 2 points which we have calculated just now. And once we find out the objective function value at these 2 points, then we use the region elimination rule to eliminate one of the region and readjust the lower and the upper boundary. Once we readjust, the width or the length of the new boundary or interval is going to be this. Now in this calculation, in the very first iteration, we did not have any previous points, so we need to find out the function value at the both location. However, in the subsequent iterations, we'll see that one of these point is going to reappear again and again. So we eventually end up estimating the objective function value at only one point which was not there in the previous iteration. Now once we complete this step, we move to the next step where we find out the precision of the boundary. So which is my present boundary is LW, and if we multiply with the original L, then we can easily obtain the present interval within which my optimum solution is going to lie, and if that is less than the precision value, then we can easily terminate, or else we need to go to the step 2 and repeat the process till we reach this condition and terminate. And once we terminate, we report the upper and the lower boundary or AW and BW as the boundary within which the optimum solution is going to lie. Now let us look into this algorithm through an example. In this example, we need to minimize this objective function. It is the same objective function we had used in the previous two methods, which was interval halving method and Fibonacci search method. And we are retaining the same, or we are using the same interval of 0 and 1, and the precision we are using the same as 0.2. So in the golden section search method, first we need to find out the W, which is now expressed as this. So W is also, it is clear that W is expressed with respect to x, and in this we are finding AW is equal to 0, BW is equal to 1, LW is equal to 1. Then we are estimating the first point W1, which is 0.618, and W2, which is going to be 0.382. If we want to find out the x value at this, we can simply use this equation to find out the x1 and x2, and we can use the original objective function value, which is this one, or if we convert the original objective function with respect to W, then we can use that as the function here to obtain the objective function value at the 2 point which we have estimated just now. And once we find out the objective function value at these 2 points, we can clearly see that this objective function value is better, so we need to retain this side. However, this side is not good, which means any side below this we can, or on the other side we can actually eliminate, and hence this side was the 0.382, and prior to that we had 0, so we can move the boundary from 0 to 0.382. We retain the other side boundary, Now the width or the length of the boundary is going to be 0.618. If we subtract, using this we can move to the next iteration. So the subsequent iterations, or all the iterations, we are going to show you in a tabular format. In this you will see that, as we had said, this is our objective function, this is our interval, and this is the precision we want to achieve. And once we map the lower and the upper boundary, which is 0 and 3, to 0 and 1, then we can estimate the two W values. One is this one and the second one is this, and at those 2 points, if we find out the function value, if we convert those 2 points in terms of x, for our better understanding we are keeping it in the terms of x. These are the 2 points in terms of x, and if we find out the objective function values, we are going to obtain this value and this value. It is clear that the optimum point, particularly in this minimization problem, is not going to lie anywhere prior to this particular point. So we can move our boundary from 0 to this point. Hence our new boundary is going to be this one and this one. And if we look into the length of this boundary, which is going to be 1.854, which is higher than the precision we intend to achieve, hence we need to move to the next iteration. At this iteration, as we are saying, the revised boundary is 1.146 and 3. And for this revised boundary, again, if we try to find out the 2 points in terms of W, then we'll find one point is 0.618, the other is 0.764. So this 0.618 is the same point which we had in the previous iteration here. So the corresponding objective function values, we can use it in this case, which was negative 49.039. We are retaining it here. So we need to find out the objective function value at the new point which we have obtained in this iteration, which is 0.764, and the corresponding x point is 2.292, and the objective function value is this. Now if we compare the objective function value, it is very clear that the optimum solution is not going to be any point beyond this new point. Hence we are revising the boundary of the upper boundary as 2.292, and again, once we find out the length of the boundary with the revised one, we can see that it is 1.146, which is still higher than the precision we want to achieve, and hence we need to move to the next iteration. And as we follow through these iterations, we can see that the boundary is moving in from one side to the other. For example, in this case, we moved our boundary from the upper boundary from 3 to 2.292. In the next case, we are moving the lower boundary from 1.146 to 1.578. Then once we go to the next iteration, we are seeing that again we are moving our lower boundary from 1.1578 to 1.854. So that is what we are showing here. Now again we find that our length or the width of the interval is still higher than the intended precision. We move to the next iteration, and this time we see that the upper boundary is being moved to the value from 2.292 to 2.124. So this is my revised upper boundary. With this revised upper boundary, if we go to the next iteration, we will see that the 2 points which we have are 1.956 and 2.019. At these 2 points, the function value or the objective function value indicates that we need to move this boundary 1.854 to 1.956. Now the boundary are 1.956 and 2.124, and the distance between the boundary is 0.168, which is lesser than the precision we want to achieve, and hence we can stop our iteration right here, and then we are reporting that the optimum solution is going to lie between 1.956 and 2.124. The midpoint of this boundary is 2.040, so we are saying that the optimum solution or optimum objective function value is expected to be negative 49.918. Now in this process, you can see that in the very first iteration we estimated two function values, in the second one 1, next is 1, another 1, another 1, and in the last iteration one more. So total it is 2 plus 1 3 4 5 6 7. So we evaluated 7 functions. Now let us look into the graphical representation of this solution. So here again the objective function is represented between 0 and 1. So initially my lower boundary was 0 and upper boundary was 3, and once we look into the intermediate points, we find out that our first x1, or in the first iteration the x1 is going to be 1.146, which is going to be here, and the x2 was 1.854, which is going to be somewhere here. And if we compare, then it is very clear to us the optimum solution cannot lie on the left of this point, so we can eliminate this region. Now with the revised boundary, the lower boundary is here and the upper boundary is here. The next point we find that the x1 is going to be 1.854, which is exactly here, and the x2 is going to be 2.292, which is here. And if we compare, we see that the objective function value at x2 at this point is higher than this point. Hence we can conclude that the optimum solution is not in the region which is indicated with the hash sign. So we can eliminate this region. Now in the next iteration, when we are looking into the lower and upper bound, the revised one, and find out the 2 points, we find one of the point is 1.578, which is going to be here, and the second point is 1.854, which is already here. And when we compare the function value, we see that the function value at 1.854 is better than the function value at 1.578, which indicates that the optimum solution is not going to be on the left hand side of this 1.578, and we are moving the lower boundary to this new point 1.578. In this revised boundary, again if we find the 2 points using the golden section search or using the golden number, we'll see that the point is going to be at 1.854 and 2.019, which is going to be here. And if we compare the objective function value at these 2 points, we find that the objective function value at the new point 2.019 is better than the objective function value at 1.854. Hence, we can eliminate the region on the left hand side of the point 1.854. So the new lower boundary is 1.854 here, and this one. Within this, once we find the 2 points, one of the point is going to be 2.019, which you already know from the previous iteration, and the new point is 2.124. Again, if we compare the objective function value, we'll see that the objective function value at 2.124 is higher than the objective function value at 2.019. Hence, we can eliminate the region which is on the right side of the 2.124. So we are eliminating this region. Then we are moving the upper bound to this new place, and then if we are searching for the 2 points, we'll find the 2 points are going to be at 1.956, a new point, and the old point 2.019. And if we compare the objective function value, we find that the objective function value at 2.019, which is here, is better than the objective function value at 1.956, which is here. Hence, we are eliminating the region on the left hand side of 1.956, and once we eliminate, we'll find that the lower boundary is shifted to this, and the distance between the lower boundary and the upper boundary is less than 0.2. Hence, we are terminating the algorithm here and reporting these 2 points, which is 1.956 and 2.124 as the boundary points of the optimum solution. And as you can see here, the number of objective function value evaluations required are 1, 2, 3, 4, 5, 6 and 7. So we evaluated 7 objective function values and we obtained this solution. Now, if you look into the area which is being eliminated in each iteration, you will see that in each iteration we are eliminating about 38% of the area. Now, this area or this region is similar to the Fibonacci search method. Matter of fact, the Fibonacci search method, if the number of function evaluation is very high, is going to be as efficient or is going to yield the similar result as the golden section search method. However, as we had indicated, the Fibonacci search method requires estimation of the Fibonacci number, which we do not need to do in case of the golden section search method. As the golden section search method, the number 0.618 is predefined and we can use that number again and again to estimate the new points where we have to find out the objective function value. So as we are saying that in this case we are eliminating 38%. However, if you recall or if you remember, we could eliminate 50% of the search interval in case of interval halving method. So if we want to see if we can tweak the interval halving method to some extent and obtain equivalent solution, then it is going to be good because we can actually eliminate 50% of the interval in each iteration. And if we can use certain techniques, for example, in case of Fibonacci search and in case of golden section search, we were evaluating or we were comparing only two objective function values to eliminate one of the regions, whereas in case of interval halving method we had to evaluate two objective function values at the new 2 points and compared with the point which was retained from the previous iteration. So total we were comparing three objective function values to eliminate 50% of the area. So instead of evaluating or instead of comparing three objective function values, if we can compare only two objective function values and still if we can eliminate 50% or very close to 50% of the search interval, then definitely we can reach to our intended result faster. So with that intention, we'll look into the next method, which is known as dichotomous search method. So in the dichotomous search method, we intend to eliminate about 50% of the search area which we had seen in case of interval halving method. And this can be achieved by choosing 2 points very close to the midpoint of the search space and compare the objective function values of these 2 points. Now, if we choose the 2 points on either side of the midpoint of the search interval, then we can compare and eliminate one side. That way we can eliminate very close to 50%, and if these 2 points are very close to the midpoint, it is going to be even very close to the 50% area. So for this reason we are saying that if these 2 points are of delta distance apart, which means they are going to be of delta by 2 distance from the midpoint, then we can eliminate about 50% minus delta by 2 amount in each iteration. And if we are doing this for the n number of iteration, we can clearly say that the region which is being retained is going to be of this value, which is L0 by 2 to the power n plus delta times 1 minus 1 by 2 to the power n. Now if this is the level of precision which we want to achieve, then we can easily stop at that particular point, or else we again have to keep doing that. Now let us look this thing. Now let us look into the dichotomous search algorithm for the minimization problem. So in this algorithm, first we are setting the counter or iteration I is equal to 1. Then we are choosing a very small number epsilon to represent the precision of the result we want. And we are also assuming a sufficiently small number delta to represent the 2 points on either side of the midpoint. Then we are finding out the length of the interval by using this formula b minus a in the very first iteration. Then we are finding out the two neighborhood points of the midpoint, which is going to be, one is x1, and this can be obtained by adding the midpoint from the endpoint and subtracting del by 2 amount from that point, and the second point we are adding the del by 2 from this point. So if you have to visually understand this, if this is my A, this is my B, we are saying the midpoint is here. From here we are saying that we want to move little bit on the left hand side, which is about the distance del by 2. We want to move little bit on the right hand side, which is the distance del by 2. So this is become x1 and this is going to be my x2, and we are comparing the objective function values at x1 and x2. So for that reason we are finding out the objective function values at those 2 points, fx1 and fx2. Then we use the region elimination rule to either eliminate this part or this part. Whichever part we eliminate, we retain the other part and apply the same process again until we reach the intended level of precision. So for this reason we are estimating the remaining portion using the formula which I had shown you in the previous slide, and then this remaining region we are comparing with the precision. If it is greater than that, continue. So there is an error here, we have to say set I is equal to I plus 1 and we have to go to step 2. Else, if it is smaller than that, if we say else, then we need to terminate. So if it is the new interval length is greater than the precision level, we have to set the iteration or increase the iteration by 1 and go to step 2, which is here. We are again going to find out the 2 points which are very close to the middle of the new interval and find out the function value and then eliminate one of the region. So that process will be continued from step 2 until we have the situation where the remaining interval is less than the intended precision, and once we reach there, then we are saying that we need to terminate. Now let us look into this algorithm through an example. Again, we are choosing the example of the previous method where we want to minimize this objective function within an interval 0 and 3 for a precision level of 0.2. So in the very beginning we see the interval length is 3 and our interval counter is going to be 1. So it is going to be 1 and we need to assume a very low value or very low number based on which we are going to deviate from the middle point. So in this case we are choosing the delta value as 0.001. For this value, the 2 points we can obtain based on the existing boundary is going to be 1.4995 and 1.5005. In this case, the objective function values at this new point is going to be negative 41.267 and negative 41.295. So it is clear that the optimum solution is not going to lie any point prior to this particular point. Hence we are shifting our lower boundary to this point 1.4995. The upper boundary remains there, and if we find out the interval Now it is 1.5005, which is actually greater than the precision level we want to achieve. Hence we are moving to the next iteration, where we are increasing the iteration counter by 1. So now the iteration is 2, and we'll follow through that process. Now this solution process we are presenting in a tabular form. In this tabular form, as we said, the objective function is here, the interval is here, and the precision level is here. In this case, our lower boundary is this and the upper boundary is this. The midpoint is going to be 1.5, and if we move little bit, that is delta by 2 on the left, the point is going to be this, and if we move little bit, that is delta by 2 on the right, the point is going to be this. The objective function values at these 2 points are this and this. From this it is clear that the optimum solution is not going to lie any point before this 1.4995. Hence we are moving the lower boundary to this new point 1.4995. We retain the upper boundary. At this point we see that the length of the interval is higher than the precision we want to achieve. We move to the next iteration, and once we move to the next iteration, our lower boundary is this, upper boundary is this, and based on these two lower and upper boundaries, if we find out the midpoint and move little bit on the left and the right of the amount delta by 2, we'll find the new 2 points are going to be this and this, where the function values are shown here and here. And looking into the function value, it is clear that the optimum solution is not going to lie at any point higher than the 2.25. So we are moving the upper boundary from 3 to 2.25, and again we are finding out that the width of the interval is 0.7505, which is higher than the interval which we want to achieve. We move to the next iteration, and the next iteration, based on the revised boundaries, we find out the 2 points which are very close to the middle point of the new boundary. And looking into the function values, we can clearly say that the point is not going to be, or the optimum solution is not going to be on the left side of this 1.874. So we are moving the lower boundary to 1.874. The width of the revised boundary is still higher than the precision we want to achieve. We move to the next iteration, where the lower boundary and upper boundary are revised. We are finding out the midpoint neighborhood points, which are these two, and the function values are going to be these two. And comparing the function value, we can say that we need to move the upper boundary to this new point 2.0625, and once we move and estimate the length of the interval, we find that it is less than the precision we want to achieve. So we are terminating and reporting the new boundary as my optimum point location, where it is going to lie. So we are saying that approximately the optimum point is going to lie at the middle point of the upper and the lower boundary, which is going to be 1.968, and the function value at that point is going to be negative 49.95. Now if you look into the number of function evaluations in this case, we'll find that we have evaluated 2 here, another 2 here, another 2 here, another 2 here. Total it is 8, and in these 8 function evaluations we were reducing the we were eliminating the search interval about 50% in each iteration. So just looking into the number of function evaluation, this is little bit higher than the or slightly higher than the golden section search method and Fibonacci search method. However, this is lower than the interval halving method. If you recall, for the same function and the same precision level, we required to evaluate 9 function evaluation, or we need to evaluate the function 9 times in case of interval halving. So definitely it is lesser than the interval halving. Another thing, if you notice in the golden section search method, we had to estimate W and then convert that W value to X and then again find out. So this conversion, again, there are certain function evaluation or rather function estimation. So even though that is a very minor one, but it is going to increase the computational. In this case, it is going to increase the computational burden. However, in this case, we do not have any such requirement. We are actually only estimating 2 objective functions, nothing more than that, apart from the 2 points we are finding out. So now let us look into this solution in a graphical format. So in the graphical format, this objective function, which is represented between the lower boundary 0 and 3, first we are looking into the point which is very close to the midpoint. So we looked into 2 points very close to this midpoint 1.5, and we looked into this 2 point. We found out that the objective function is not going to lie on the left hand side of this point, so we are eliminating any region on this side. Then my revised boundary is going to be from here to here, and if we look into the midpoint of this, it is going to be somewhere very close to 2.25. So we looked into 2 points which are very close to 2.25 and realized that the objective function values on the right hand side is going to increase, hence the optimum solution is not going to lie at any point on the right hand side of this point. So we eliminated that region. Now our boundary is going to be between 1.5 and 2.25. So then we are looking into the another midpoint which is very close to this point, which is about 1.75, and the 2 points in the neighborhood of this 1.875, we find out that by evaluating we can clearly see the optimum solution is not going to lie on the left side of this place, so we are going to remove this space and the lower boundary is moved to this particular point. Then with the new interval, once we look into the middle point, the 2 neighborhood points, which is going to be somewhere here, and from this we can clearly say that the optimum points is going to lie between this and this, but not on the right hand side, so we can eliminate this, and hence we are reporting that my optimum point is going to be between 1.874 and 2.0625, and we reported the optimum solution somewhere at the middle here. Now if you look into the number of functions, at this point we evaluated 2 functions, delta by 2 on the left, delta by 2 on the right. Again at this point we evaluated 2 points, then we evaluated 2 at this point and 2 at this point. This is how we evaluated total 8 objective function values at those 8 points to achieve or to come closer to the optimum solution. So this is how the dichotomous search method works. So today we learned about 2 more region elimination methods. So altogether we learned 4 different region elimination methods. Now if you recall, we said that first we are going to use the elimination method where we are going to bracket the optimum solution using one of the methods we had discussed earlier, and once we do the bracketing, then we use the another type of elimination methods which is known as region elimination method to come precisely close to the optimum solution of the problem. There are other methods to come closer to the optimum solution. Those methods are known as interpolation methods. In the next class onwards, we will be discussing about the interpolation methods, and some of this interpolation method requires derivatives and some does not require the derivatives. So we'll start the interpolation methods with and without derivatives from the next class onwards. So till then, thank you and see you in the next class.